This is Lab 4, which goes over circuits and capacitors. So on the left, you see the circuit that I created. So I found a consistent current of 0.02 amps no matter where you put the ammeter around the circuit, which makes sense as current should be constant in a connected circuit. And then on the right, you can see where I found the voltmeter readings of the potential difference between different components of the circuit. So each battery contributed 1.5 volts of potential difference. And then the first resistor reduced that potential difference by about 0.99. And then the second resistor, which had a stronger resistance, reduced it by about 2, back down to 0. So the total potential difference for the system was 0. The first part of the RC circuit experiment, I set up a circuit with a 9-volt battery, a 10 ohm light bulb, and a 0.2 farad capacitor. I then timed the charging of the capacitor with the battery in series, and then the discharging the capacitor when you removed the battery and connected the wires. And then I repeated this with the 12 ohm bulb. So what I found was that the charging and discharging was a lot faster with the 10 ohm light bulb, which makes sense because the RC constant is resistance times capacitance. So with a higher resistance, the amount of seconds that it's going to take for that significant discharge is going to be greater. So if you take the voltage that was found at each second divided by the initial voltage and take the natural log, compared to time, it creates a linear plot. And that is going to be equal to -1 over the RC constant. So you can take the slope of that line and solve for the RC constant. So what I got was 5.999 seconds. Now, theoretically, RC is resistance times capacitance. So the total resistance was just the light bulb, which was 30 ohms, and then the capacitor was a zero point 0.2 farad capacitor. So that would be a prediction of 6 seconds, which is really close to the 5.999.